Okay, so this is the second half of this photon section where I'm going to do more of the practice problems and talk about some of the calculations and things that are involved. And basically, as you'll see, almost every problem is going to use really only two equations. We're going to be using the Einstein relation for energy of a photon, and you're going to be able to relate wavelength and frequency with the speed of light. And that's really it. There will be other calculations involved, but those are really the only two equations that we're going to be using. So this first one, we want the energy, and we're given the wavelength, and so that's just putting these two equations together. And that's a really common thing, so it's kind of handy just to remember, right? If I put these two together, I get this, right? HC over lambda. And so that's a handy one, just because a lot of times you're going to have wavelengths and not frequencies given, just for whatever reason, sort of, I guess, experimentally or conceptually. Most of the time, wavelengths are what's reported, not frequency. So most questions will involve a wavelength. Also, this HC product is actually on the AP sheet, so that can save you a little bit of time. So we need the energy for that wavelength, so we'll look up H and C, and we'll plug in 550 nanometers. That means, right, we have to convert this to 550 times 10 to the negative 9th meters, right? And then we just plug it in. So that's part A. Part B, we are told the 1 joule every second. And that one is really a unit conversion. They're gonna show it one. I'm gonna do it a slightly different way in just a second. Let's look at the work, and I'll talk about it as we go. So, right, they calculate the frequency, and then they use the energy relation from Einstein's to calculate the energy of a single photon. Right? Notice the units are joules. If you wanted electron volts, I think that's the next conversion. It's just a unit conversion. It's on the AP sheet. Right? You don't necessarily need to do that unless it asks. Either joules or electron volts are acceptable. So the second part, right, is that we want the number of photons when we have the number of joules and the joules per photon. So it's really, think back to chemistry, it's a unit conversion problem. So here's kind of how I would set this up. It's a little bit different than the work they have. Right, we have 1 joule of energy, and we know we have 3.6 times 10 to the negative 19 joules in 1 photon, right? It's like a ratio. And so the joules unit cancels, and you can see that that's the mathematics they do right there, and the units are correctly photons. And so, right, this is a lot of photons. This is why I said in the previous video that everyday experiences deal with so many photons that you always fulfill that third postulate, that you have sufficiently large number that it's indistinguishable from a wave. It's only when you're trying to create a situation where you have a very, very tiny number of photons that you're ever going to see some of these odd effects, right? 10 to the 18th photons is a lot. Okay, so now we go to the next practice problem. Okay, so this one reviews a little bit of stuff from the early part of the year with electrostatics, right? We have a potential difference, and we want to figure out how much energy that electron gets, because we're going to give up whatever the energy the electron gets and turn it into an X-ray, right? If I knew the energy the electron has, I know the energy the light photon gets. Then I can use, right, let's do it like this. So E photon HC over lambda, right? So I can find, if I know the energy of the photon, I can get the wavelength. But, right, we're saying the electron gives up its energy, so E electron must equal E photon. And so now I just need to figure out, how can I calculate the energy of the electron? And that comes from the potential difference, which hopefully you remember is Q times V, right? And Q there is the charge of the electron. So what we're left with when we put all these together is QV equals HC over lambda. And I've rearranged to solve for lambda. And Q is really E, right, the charge of the electron, right? And then I just plug those numbers in, right? H, C, and E are all on the AP sheet, and the voltage is 50 times 10 to the third volts, right? Again, you have to convert the units. And if you plug all that in very carefully, you get 2.48 times 10 to the negative 11th meters. And this should be encouraging, right? Look, this is an X-ray, right? This is around 100th of a nanometer in terms of wavelength, right? Much shorter than visible light. That makes sense for what we know X-rays to be. So it sort of checks out. Okay, so here we have a cell phone frequency. We want the wavelength and the energy. So for the wavelength, we use C lambda times F. And if you solve that for lambda and plug in the values, notice this giga prefix is times 10 to the 9th. It's a billion, right? And so lambda is going to be 0.16 meters if you plug everything in correctly. For energy, right, we need E equals HF, and we have the frequency. So that's, again, just make sure to do the gigahertz unit conversion. And if you plug that in, you get 1.3 times 10 to the negative 24th joules. So, and then the last step is similar to the first problem we did, right? 0.60 watts. This is 0.60 joules in 1 second. And so we can just kind of do this as a unit conversion problem, right? 0.60 joules in 1 second, and then 1.3 times 10 to the negative 24 joules in 1 photon. And sure enough, right, those joules unit will cancel, and we'll be left with photons per second, which is exactly what we wanted. So now we can do 0.6 divided by 1.3 times 10 to the negative 23rd. And if you do that correctly in your calculator, you get times 10 to the 23rd photons per second, right? Again, a huge, 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 huge number. Notice that this is right, this is radio waves. And so this is why you get so many more photons in a radio wave, right? Each photon has less energy, so we need more photons, unlike the X-ray example previously. All right, moving on to the next one. Okay, so here, right, we have the power of a laser pointer and the wavelength of a laser pointer. This is a pretty standard laser pointer. This is pretty equivalent to the ones that I used in class. And we want the photons per second. And so this is right here. This is what I want you to be thinking about in the steps. Like, how can we relate all these things together? So they've kind of already written it, right? We use the power to find the energy every second. Right? This is 1.0 times 10 to the negative third joules in 1 second, right? The definition of a watt is a joule per second, and then the little m is milli, 10 to the negative third, right? This we can use to find energy of a photon, right? And if we know the energy of a photon and the energy every second, we can then do what we have done for other problems to figure out the number of photons every second, right? So this is them working it out, right? They calculate the frequency, they calculate the energy. So there's our energy of each photon, right? Now, right, this is the unit conversion sort of all done in one line, but it's the same thing, right? You divide, right? The energy, the total energy and the energy in a photon tells you the total number of photons. And so we get 3.4 times 10 to the 15th photons every second. And you notice even with a relatively weak laser, right, that is still a huge, huge number of photons, right? This is why we don't see these quantum mechanical effects. Okay, so the next one, right, now this is a sort of a connection to some circuitry stuff. So a lot of this, again, is going to be familiar, right? We have the 1.0 joules per second. There's our energy every second. And we have the wavelength, so we can find the energy of a single photon, right? Notice, right, monochromatic means only one wavelength or only one color. And then we have to remember a little bit about the photoelectric effect, right? And that's this statement right here, right? Each photon can give its energy to one electron. So for every photon that this sort of first situation describes, that this part right here describes, we'll get one electron that's moving. And if we know how many electrons are moving, right, we can use the definition of current is coulombs per second. If we know how many electrons are moving and the charge on an electron, we can figure out how much charge is moving, right? That's back to some circuitry stuff. Okay, so let's work these out bit by bit. So our first step has got to be figure out how many photons do we get from that first bit of information. That's the part we've already done before, right? So we get the frequency and the energy of an individual photon, and then we calculate, right, the total energy divided by the energy per photon to get the photons in every second. That tells us then that we have this many electrons flowing every second at most, right? Realistically, you're not going to get perfect efficiency here. But at most, we get that many electrons that flow. And then all we need to do is convert the number of electrons to a charge using the charge per electron. That's on the AP sheet, right? This is the constant E, the charge of an electron. And so if we multiply those out, then we get a coulombs per second, which by definition is an amp, and that's a current, right? So you get about half an amp or so at most. Okay. All right, now on to the next, eventually, the next one here. So we have 2 more left. And so this is again, right, it should look very familiar, right? We have the energy as a wavelength. We're going to use E equals hc over lambda. We have 2 wavelengths in this problem, right? And so we want the energy for each of those types of photons. So we look up those values for H and C on the AP sheet. Remember to convert nanometers to meters, right? Which is 10 to the negative 9th. And so if we plug that in, we're going to get the energies for these 2 photons as follows. For the 313 nanometer light, we're going to get 6.4 times 10 to the negative 19th joules. And for the 280 nanometer, it's a little bit more energy, 7.1 times 10 to the negative 19th joules, right? And then the second bit, right, total photons, right? Here's our energy limit. We have a total energy and an energy per photon. So it's the same process as we've done, right? Just E total divided by E photon equals N photons, right? And since we have different total energies and different energies for each photon, we need to do both of them completely separately. If you do that carefully and correctly, you will find that for the 313 nanometer light, since it's got less energy per photon and more total energy allowed, that you get an exposure of 7.8 times 10 to the 17th photons for 313 nm. And the 280 nanometers, right, much less energy is allowed, and each photon is more energetic, so we get a smaller number, about 4.8 times 10 to the 15th photons for 280 nanometers. Okay? Okay, so this next one, right, again, should not look very different. We want to know the power, which is a joules per second, for a laser pulse. Well, we have the energy and we have the time, right? It kind of cut off oddly, it's milliseconds. So 7.0 joules over 1.5 times 10 to the negative 3rd seconds, right? That's a power. And so that's pretty quick to plug in, and you get 4.7 times 10 to the negative, or not negative, the positive 3rd watts, right? The negative 3 is in the denominator. And then once again, right, we want to know how many photons. We know the energy of a pulse, and we know the wavelength, so we need the energy of a photon first, right? So we can calculate that out with that wavelength. The energy of a photon is 3.4 times 10 to the negative 19th joules. And then we just do 7.0 joules divided by the energy of a single photon. And if you do that correctly, you should get 2.1 times 10 to the 19th photons, approximately. And so you can see that, right, I've really only used 2 equations for every single one of these problems. Every other calculation I did was sort of remembering some definitions from previous parts or some sort of unit-based reasoning. And that's really the core for photons, is recognizing that you can calculate the energy by given the wavelength of the frequency and then use that energy just like any other energy.